My name's Hamish and I'm an FPer. I've been around the functional programming community for a while, but this is actually my first time speaking at a FP conference. I'm an engineer at DriveTribe, which I'll talk about in the talk today. There's some quite nice examples. And along with FP, I spend most of my time worrying about data things and machine learning. I'm also on Twitter, which is predominantly photos of my cat. So, but feel free to follow if you like cats. Not, the library. So I'm going to do something a bit weird, and I'm going to talk about distributed systems at an FP conference. So I'm sure you know this, but there are generally three things you want from any distributed system. We want partition tolerance, which just means if we start losing nodes in our system, we're going to stay up. It's also kind of undesirable as a user using a system if you get a different response depending on what node you hit. So we always want this thing called consistency as well. And we also want availability. So we always want to get a response. And I'm sure everybody in this room knows, but there's this thing called the cap theorem, which says, in general, you can't have all three of these things all the time. You have to make a decision between two of them. So in general, any system that doesn't have partition tolerance is kind of terrible. Like, this is the kind of system that wakes you up at 3 in the morning because something's gone down. And as developers, we don't like working on those systems. So you always want that. Which means we have to pick between consistency and availability. And we call these CP and AP systems. And I'm going to mostly talk about AP systems today. But the trade-off here ends up being, do you always want to have the most up-to-date response or an error? Or do you always just want to get a response? And you could potentially get some stale data. And why is this? And there are a few reasons, but the one I'm going to talk about today is we need to start sending messages between the nodes of our system. And unfortunately, that involves networks, and networks are rubbish. All kinds of stuff goes wrong all the time. And I'll argue that most distributed systems that you use as an end user are AP systems. In fact, it's kind of hard to think of a CP system that you would use as a user. And there are a few reasons for this. The first one, particularly as an FPer, is this erroring thing is kind of scary. Why should I care that the server's busy thinking and trying to agree on what data it should have? And in reality, we don't often need strong consistency. So if I'm sat there on Twitter next to my mate and we're both looking at the same profile, how often do we check how many likes somebody has at the same time? It's kind of weird. We don't really do that. And we can also design these AP systems to be eventually consistent anyway. So this consistency issue is kind of a non-thing. So let's talk about eventual consistency a bit. We can actually prove that an AP system will eventually become consistent. And there's a bunch of different ways to do this, a bunch of different techniques. But the sort of most common approach that people are using at the moment is a thing called a CRDT. And this paper at the bottom is the CRDT paper. It's like 15 pages and really not very intimidating. So I'll share these slides at the end. And the way that CRDTs work is really simple. They basically just let these failures happen and then fix the conflicts later. And what's really cool about them is they can do this fix-up process independently. And to do this, we need some kind of merge process, which I'll talk about in a minute. But this merge requires just three things. It needs to be associative. it needs to be commutative, it needs to be idempotent. I'm at an FP conference, so I assume everybody knows what this means. Okay, cool. So while preparing this talk, I actually discovered that this pre-exists CIDTs, this idea. And it was in this paper, they called it ACID 2.0, and it's really obvious that this distributive thing was just added to spell the word acid. So if you actually read it. Okay, so I'm going to take a real gamble now. So this sounds like some sort of FP thing. So we go to our favorite algebra website. I wasn't sure if that was going to load. And we look up what has these properties in the table. And of course, this is a semilattice, which is pretty cool, right? We've found this thing that we know how to deal with at the system level. So I'm not going to really talk about this, but I think it's really interesting that as a community, we're really, really good at talking about things at the micro level. We're like fantastic about talking about building this pure function that we can compose with this pure function to build something amazing. What we don't really ever do is talk about how these same concepts are seen on massive scales. So, and like how we can drill down a bit. So what kind of implementation do we need for a semilattice? Well, I mean, the sort of dumb first attempt is addition over the integers, which is associative and commutative. It's not idempotent, obviously. So we kind of can try the sort of standard thing that is idempotent, which is just union over sets. I'm sure you know all this, but I'm going to use it soon, so I just want to cover it. This is associative, it commutes, and obviously it's idempotent. That's what we wanted. And for the rest of these slides, I'm going to use a set as the CIDT structure I'm going to use. In reality, if you're building a big system, you probably want to use something a bit sexier. You probably want to use a hyperlog or something. And that's for space reasons. Okay. So let's go through an example. The canonical example of this kind of thing is Google Docs. And everybody knows Google Docs, right? So I'll start typing something and I'll share the document with Chris. And Chris will see it straight away. He'll start typing, I'll see it. So imagine we have 3 people. We have Alice, Bob, Drunk Pete. And this is the only funny slide, I'm sorry. And we have Alice make some change. And what happens is Alice sends a message to the other nodes saying, hey, I did this thing. And the other nodes get updated with it. Then later Bob makes the same, like another change. The same process happens. Alice gets it. But Drunk Pete never gets the message. Maybe fell over or something and broke his laptop. So Pete's now in a stale state, and this needs to be resolved. And what happens is later, Alice will try to repopulate, and what she'll say is, hey, these events happened. This is the set of events that I know about. And obviously because this is idempotent, and it commutes, Bob already has these events, he doesn't see any change. But Pete, on the other hand, he hasn't seen event B yet, and he'll merge this set into his current set, and he'll have all the events. So this is fine, this is okay, but how often do you actually ever, in practice, have this problem? Not many of us work on distributed databases design or anything like that. So does this actually happen in the real world? And actually, yes, this happened to us at Drive Tribe. And we had to resolve it. And I'll explain why. Come on, yeah. So this is Drive Tribe. Half the reason I was scared was if DriveTribe was down, the number of people that would fix this site are in this room. So, so DriveTribe is a motoring website. It's for people who are really into motorsport or cars and all this kind of thing. And it's founded by the Top Gear guys, Clarkson, Hammond and May. And we have the normal sort of social media things. It's not responding. So we have posts that can be liked and commented on and all this kind of thing. And our architecture looks a little bit like this, which is kind of unusual. We have this CQRS event-driven system where we treat reads and writes differently. So events are basically king in our system. What happens... Oh, actually, I'll just skip to an example. This is heavily based on a blog post by Martin Kleppmann called Turning the Database Inside Out, which is fantastic. And he's just released a book called Designing Data-Intensive Applications, which is probably going to be one of the main books that everybody starts talking about in terms of system design. So let's go through an example, right? So Alice comes to DriveTribe, and she sees some post. And what happens is she hits the REST API, and the REST API goes to Elasticsearch, and it says, hey, get me the data for this post. And this post has 720, we call them bumps, but likes. That's the way you should think about them. And she goes, okay, I want to also like this post. So she'll create some event, a like event, which hits our REST API. Instead of going to the top part of this architecture, it goes to the bottom part. And Dominic, I think it is, talks a bit about Kafka. We heavily rely on Kafka. Kafka's, if you don't know, who doesn't know what Kafka is? That's probably the easier question. Okay, so it's kind of it's just a big immutable log. That's how you think about it. And we use Kafka as our source of truth for everything that ever happened. And every event that happens from a user ends up in this. So Alice creates a like event, it ends up in Kafka. And then we have this really powerful stream processor called Flink, which is kind of like the nuclear warhead of stream processors. And this will read from Kafka, and it will transform this event into something that a front-end developer would accept. They normally don't like to just receive a stream of events and be told, hey, render this. Instead, they like to have like JSON packages and stuff. So we create a new event, and we create a new view from our stream processor, and we store this in Elasticsearch. And then the next person who hits this post will see 721 things. And this is kind of a normal, well, what I consider a normal CQRS system. And this is cool, right? Except this is the exact same problems as the Google Docs example. And that's basically because of networks. And maybe the odd bug. But fortunately for us, it has the same fix. So we can use Semilattices. And the proof for this is a little bit gnarly, but I can give you a really good visual example of why this is true. So if we go back to our Google Docs example, and we have Alice, Bob, and Pete all sending events to each other, and we just sever this connection. That means Pete is now solely responsible for obtaining events, resolving any conflicts, and sending back what the truth is. And this merging process that we talked about before, it was independent of any structure. So actually, in reality, Pete could have some slightly crazy internal structure like this, and there's actually nothing stopping that being scaled out horizontally and being its own big system in itself. And now we have a big system that can resolve these conflicts. And I know it's really hand-wavy, but actually, if you follow what the proof is, it kind of actually does this. So someone asked earlier, who knows Scala, and everybody stuck their hand up. Who isn't a Scala developer in the room? Oh, awesome, so quite a few. Okay, so I was really paranoid while preparing this talk that I was, like, most of the room weren't going to be Scala developers. So I've tried to avoid code so far. But I'm just going to ignore that now and show you anyway. And to do that, I want to walk through an example about how we use this semi-lattice in practice. So let's go back to this post thing, and we want to start counting likes again. And we're going to do it as they come in. So we're not going to do this in a batch process. We're just going to stream as they come in. We're just going to stream them and count them. So in general, when we build these views, we don't have one thing that we care about and we want to send back to the front end. We have multiple things. So we have I've got this kind of dummy model that sort of shows that a bit. I don't know if you can see because it's quite small, but this post has like 150,000 views. And this is the kind of thing we send back to the client as well. We also need some kind of like model. So the dumbest thing you could like implement, especially just to show the idea for a conference, is just some like post ID, user ID pair. Like, it's kind of the simplest like you could have. And the plan is we're going to, this code is going to live in our crazy stream processor. And for this example, we're going to cheat and only consider events of one type of one post. So we're going to read a like event out the queue, and then we're going to transform this into sort of a dummy post stats view, sorry. And then we're going to just we're just going to fold this as new elements come into as new events get read off the stream. Okay, so to do this, we need a semilattice. And in Scala, we encode these with implicits, which by the first like 3 or 4 talks, you must know by now. All we have to do is have an implicit of semilattice, post stats, and scope. So how do we define this? Well, this is kind of easy to implement. In fact, I think it's just this is union over sets. This is kind of, I think this is the default implementation. If you use anything like cats or Scala's Edge, you would get this implementation. This actually has the same semilattice, and I don't really want to go into the way that stream processors work, but through a hack of the stream processor that we have, we can always build this as well. If you're interested, come and find me afterwards. And then if we're going to try and build the semilattice for this thing, there's kind of only one thing we can do, right? There's only one obvious implementation of this, which is to combine each element individually and just cross your fingers and hope that that's the semilattice. And this actually works. And it's actually totally provable. Yeah, I'm glad I'm not showing the proof. That if everything in your case class has a semilattice, your case class also has a semilattice. Which means you have a CRDT, and you have a happy life. Okay, so can we generalize this? So what do we actually do? Well, we didn't know how to build, it wasn't totally obvious how we're going to build a semilattice for post stats to start off with. But we did know how to build one for each of its elements. Then we, jump the gun a bit. And then we just combine them in the only way that was kind of obvious. And in Scala, we have this awesome generic programming library, which can do basically all of this for us, can remove all this boilerplate for us. And it kind of works a bit like this. So this type that we've got, poststats, this can actually be broken up into an H list. It can actually be broken up into a list of its elements. And then we can just traverse this list at compile time, searching for our semilattices. And then we can get some machinery and shapelist to just build the final thing for us. And I'm going to just show you what the compiler basically does. And then I'm going to show you the code to do this. So you basically just say, hey, compiler, I need a semilattice for this. Goes, no. But I do know how to turn this type into this H-list thing. And I know how to find this. I wonder if I can find one for this. And then you just iteratively go through the list, finding all these elements. And then we just build this back up once we have all these things. And here's the code. If you actually sit there and try and code this probably wouldn't take you very long, and this is kind of the only way you'll get this to compile. So you'll pretty much always end up doing something a bit like this. For those shapeless nerds out there, I don't actually know if you still need lazy, the latest version of Scala. I heard you probably don't. And this has three methods, basically. So this thing at the bottom, all this is doing is it's tearing down our type and then constructing the semilattice at the end. We need to define this a semilattice for this h-nil thing, which I haven't really talked about. And then this big block of code in the middle, this is literally doing this iterative search over the h-list for the semilattices and then combining them. And abruptly, that's the end. If there are any questions or anything, maybe just come find me after, because I think we've got lunch now.